Starting the streaming now. All right, so we're going to get started with today's class right now. And I'm just going to say it is kind of super important for people to be here, live, so they can ask questions interactively. Missing the live lecture is not good. I would just put it that way. And it's not just that people need to show up, quote unquote, in Zoom or in Google Meet in this case, but it's also important to ask questions, when I'm trying to explain things, especially when things are not just, well, I kind of get the gist of it. When things are go like, I have no idea what this code is doing, then it's kind of important. Um, so there is that. All right. I'm just reading the text over here. Alrighty. Okay, so I think we are okay at this point in terms of there are no questions over there, mostly just comments. Okay. All right, so we'll start with me doing the homework assignment first, and then we'll move on to certain things that are related to the simple use of struct. So we'll go ahead and uh, do things in that particular order. All right, so this is the homework assignment that was due about 5 minutes ago. And I'm gonna click on question number 3 where there's a link. I'm just kind of skipping the other ones unless people ask me about the other ones. I think the answers are known at this point, so so there's no need to kind of go through those. But if people are interested, I can always talk about that. All right. So here's the zip file, and I am going to save it into the temp folder. Replace the one that I have there already, which is exactly the same thing, and then we'll work on it. Now, if most people think there's no need to go over it, we don't have to go over this. On the other hand, if most people think this is a good idea just to go over it, even though you got your program working, sometimes it's still a good idea to kind of have me to explain it, walk through the whole thing again. Okay, all right, I'll do it. All right, so I'm just going to overwrite the 2 files, and we are going to open up the .c file on one side, and then we'll open up the TTP-ASM file on the other side. Nope, okay, that's not what I wanted. I want it to be side by side and not up and down. There we go. And I can change the dumb terminal to be a little bit wider, so this way we don't run out of space as quickly. There we go. All right. So the only thing you have to implement in this case is traverse, and traverse is relatively short compared to what we're going to do this time, and that's why you have a whole week, for the upcoming homework assignment, because it's considerably longer, and it does make use of certain things that are, I wouldn't say trickier, but it's a combination of things that we have already been exposed to. So it's a little bit different. But having this one explained first, is going to help. All right, so the first question, tonight's one, there are 2 parts. Part 1 is due tonight. Because I noticed, if I don't make anything due on the same night, most people are just going to go off and, not to work on stuff. So I'm just going to help you guys get things started. I'll put it in a very gentle way. I'm going to help you get the project started with part 1 of the activities. There we go. Yep, part 1 and part 2. All right, so the first thing is there are a few people asked me about cond as a function, about whether it is right or not. Okay, and the answer is right. The implementation looks like it is wrong, but it's actually not inconsistent with the way C interprets values. Okay, so when you look at the C code here, which says return p does not equal to 0, most people would automatically think, oh, it's going to return either true or false, right? It will return 0 or false, in one case, but then it's going to return true, when p is not 0. Well, that's one interpretation. So let me ask you, what is the representation of true in C? I'm not talking about C++, I'm not talking about Java, I'm talking about C itself. Anything other than 0, okay? Any value other than 0 is considered true. Okay, so in this case, in the C code, p does not equal to 0. So that means p is a pointer. Okay, but a pointer is nothing more than just a bit pattern for comparison purposes. So anything other than 0 is not 0. Wait, hold on a second. Tech, what did you just say? I just said anything other than 0 is not 0. So the answer doesn't have to be 1 or 0. It is 0 versus everything else. So that means if I just return p by itself in assembly code, that implementation is not inconsistent with the C code. It is not wrong. All right. So there are a few things that people asked about with cond. Okay. So now that we have got cond out of the way, we'll go ahead and actually implement traverse. All right. So here comes traverse. So we start with the label traverse, and then I typically want to look at how things look on the stack. Yeah, the volatile thing basically just tells the compiler not to be a smartass. Yeah, because a compiler, if you turn on optimization like dash uppercase O and then followed by a non-zero number, it will turn on optimization, and one of the optimizations, it will analyze how a variable is changed. And if you don't say something is volatile, then the compiler will say, hey, you change it here, and then you update it over here, and then you update it over here, but you never really read the value of the changed variable all these times. Okay, so the compiler would just say, I'm not going to generate any code except for the last update, because all of the other updates is not going to do any good. And in this case, we are just putting something into printer. There's no code whatsoever in this program that reads the value of printer, right? So to the compiler, this doesn't make sense. It does not compute. Well, technically, it does not compile. No, it doesn't. It doesn't make sense, because I'm just changing a global variable called printer, but nobody is reading that global variable. So to a printer, to a compiler, it is entirely possible that it would optimize this out entirely, and then we just end up with nothing. There won't be any printer variable to observe as the output. So that's what volatile is about. Volatile is basically saying, we can have gremlins in the background that may be reading the value of printer, for stuff. Okay, what stuff? We don't know. We're just saying that, every time we're changing printer, just change it. Okay, don't try to optimize that code out. Just change it. So that's basically what volatile is about. Well, in this context, anyway. All right, getting back to the implementation of traverse. So it doesn't have any local variables. So if I don't want to, get to all the other, definitions, we can just say p is defined as 1, because I'm defining the offset from where the stack pointer points to the parameter p. Okay, so if what I just said is confusing, or it doesn't seem to make a whole lot of sense, that means the people who think that way will have to review the material from the past, because we have been talking about how arguments are pushed on the stack in a particular order, and that is why p as a parameter is 1 byte away from where the stack pointer points to. All right, so I'm gonna turn off my okay, can't do that here. Okay, let me do something over here. All right. There. Okay, I'm just getting a lot of background dings because of some text stuff going on. All right. So there's a question of, is it okay to have the boilerplate code for variables as in traverse local var size 0? Absolutely. So, if you put in those extra definitions, it's not a big deal. I'm just, saving a little bit of typing here. All right, so P is at an offset of 1 from where the stack pointer points to. And there's nothing I need to do for the stack. There's nothing to subtract from the stack pointer because I don't have any local variables. So there's nothing to do. So what I usually do is I just start with the end of the subroutine right away. And as I have said in the previous class, okay, these 3 instructions, what each one does individually and what they do together as a whole and why it works. All of those should be understood by now. Okay, I've been explaining that has been explained a long time ago when we first talked about stack and then calling and returning from subroutines. So that was a few weeks back already. So it's kind of important. All right, so now we look at this code and go like, how do we do it? So the key is, you're not supposed to macro or inline expand, the condition over here. You're supposed to actually call the subroutine cond. So now you have to set up the loop structure first, and then we actually have to call cond with p as a parameter and so on. So we'll do that. So every time you set up a while loop, it would start with a while begin, and then at the very end, we have a JMPI back to while begin, and then we have the exit point, which is while end. Okay, so this is just the way I code it. I just like to open the parentheses and then close it right away, and then go back and insert the code that is supposed to go in between. All right. There is no passing by reference. This is regular C. There's no pass by reference. If it were passed by reference, you would see the ampersand in the parameter definition, and we don't see that. Everything is passed by value in C. Okay. So that is the sort of stuff that I expected CISP360 to teach. So if that is not the case, then we have to have some conversation with people who teach CISP360. All right, so now we are into the while loop. So we need to push P on the stack and then call cond and then clean up the stack and then check the return value of calling cond. Okay, so the first thing first, we have to push P on the stack. So LDI AP add AD LDAA. So at this point, A should have the value of parameter P. So we need to push it on the stack, which means we decrement the stack pointer and then store to the location that we just make the stack pointer point to, like that. So now we have pushed P on the stack, the value of parameter P on the stack. So it's now time to call the subroutine. And if you want to, you can always automatically put an inc d over here because we did push one parameter, so it's time to kind of pop that parameter. So in between, we have to push the return address on the stack, which is .6+. Now there are several ways, 2 ways, to specify the return address. .6+ is assuming that we are doing the decrement D after the LDI, but if you do the decrement D before the LDI, then the amount that you have to add would be different. All right, so we stda. So now we have pushed the return address on the stack. It is time to actually jump into the subroutine, which is cond, like that. When it returns, we increment the stack pointer to deallocate the argument that we just pushed on the stack. So at this point, we can evaluate the return value coming back from cond, which is in register A. Why is in register A? Well, that's the convention that I chose. Remember, this is just a convention. We just need to make sure that the caller and the callee agree on which register is used for the return value. And in this class, we use register A. So we just have to check register A. So instead of actually comparing that to 0, this is the shortcut to do it. We just do it AND AA, and then a JZI, conditional branch to the end of the loop. So while end is where we want to go when the return value is 0, which basically means the pointer is null at that point. And then we have to specify what we need to do in the loop at this point. All right. Oh, turn on the line numbers. Sure. There we go. Oh, that's the whole point of pushing the argument on the stack so that the subroutine that we are calling can use it. Yeah. Okay, I'm glad that Ryan is teaching passing by value versus passing by reference correctly, because it really is an important concept. But count itself doesn't set the flag. It is how we use the AND AA instruction that would set the flag, and we only care about whether it is 0 or not. So JZI would work. Line 40 to line 42. Okay, so on line 40 we have the displacement of where P is on the stack, but that is a displacement or an offset in number of bytes from where the stack pointer points to. And then on line 41 we add the stack pointer value to the offset, so that means A is now has the address of P on line 41 when line 41 is done. And then on line 42 we dereference the value of A. Basically we use register A to go to a location in memory and then retrieve the value of that location. So what that eventually did was to come back with the value of P, and then we put it in register A. Okay, so so any confusion about line 40 to line 42, draw a picture. Okay, draw a picture of what is on the stack, where register D is pointing to, what is the value of the label P, and that will help. Now, if that is still confusing, then it might be an issue with not understanding the mnemonics, not understanding what is LDAA actually doing. Now, that is more of an issue because at this point I am assuming that everybody understands what each instruction does in the processor. Now, what if someone says, but I still don't quite understand what is LDAA doing in the processor? Then I will refer those people to use the trick that I have used, well, not a trick, but use the technique that I have used at the very beginning of talking about the TTP architecture, and use Logisim in GUI mode and actually observe how the multiplexers and the demultiplexers are set up, observe whether RAM is active, whether a register is ready to be updated, and so on. Okay, that is the lengthy process that is inevitable in order to understand all of these instructions. There's no shortcut, to get this stuff understood. Okay, so now we got a few more questions. Is it wrong if I make register A point to label A directly instead of P? Label A. Label A. What is label A? Alright, so let's check out what is label A. It would be wrong in the context of traverse, because if you do that code in traverse, then it won't be able to move anywhere else. So yeah, so A is the address of A is passed from main, but the code of main is already given to you. So as far as traverse is concerned, it doesn't even need to know where A or B or C are, because if I change this code, which is something that I can do when I grade it, if I change this to B, or if I change this to C, the behavior of the code obviously would be different. But for people who kind of lock down the value of P P, over here and say that it's just the constant of A, those programs will not work anymore. So the answer is no to that question. It is wrong at multiple levels. It is wrong, at the level of the code. The assembly code is no longer matching. Is no longer consistent with the C code. So when I grade, for this class, I'm not only looking at the end result of whether a program works, quote unquote, works or not. I'm looking at whether the assembly language code is consistent with the C code. So that is the most important part, is the consistency between the assembly code and the C code. All right, so we got a few things. Yes, keeping track of register D is always helpful. All right. Okay, so getting into this loop, so we got the right-hand side and the left-hand side. The right-hand side is pretty simple because I'm pretty sure that I have talked about P gets P points to P already. So you just have to change, P points to P to P points to I. So I will explain it anyway. So here comes the explanation. In order, okay, so the first thing to understand, to implement this line of code, is to understand what exactly is P points to I. We are referring to the value of member I of the structure that P points to. Pretty sure I have explained that in past lectures already, but it doesn't hurt to mention that again. So we are talking about member I of the structure that P points to. Okay, so I can't do a single thing until I get P. Okay, so the first thing is to get the value of P, the parameter, which is a pointer. All right. So now we start with that. So we have LDI P A with P. Register A is fine. We don't have any return value with traverse, so all three registers A, B, and C can be used. All right, so we have the offset, and then we have the same stuff, okay, at the very beginning of this code, all the way up to line 40 to line 42, and then we have LDAA. So now register A has the value of P. So now what is the next thing that we need to do? Oh, we don't want the pointer itself. We want the structure, right? But wait, we don't want the whole structure, because you don't know what is the size of a structure. There's no way we can guarantee to fit a structure into a register. So it doesn't make sense to use another LDAA right away, because we don't know. We don't know, whether the structure can fit into a single register. So we want to figure out what member of the structure do we want, are we interested in this case? Is member I. So now we have to get to member I. And to get to member I, I'm going to use another register, let's say B, and it is loaded with X underscore I, which is the offset to member I from the beginning of a structure. That is how X underscore I is defined. Okay, so how do we combine A and B, right? Because A is basically a pointer to a structure, which is the address of the first byte of the entire structure. B, on the other hand, is the number of bytes from the beginning of a structure to the member that we want to access. So, maybe we should add these two, right? Because once we add these two, the sum becomes the address of the member in the structure that P is pointing to. So we're going to add these two. Now, which way you add is totally up to you. Whether you add B to A or A to B, like what I'm doing here, it's okay. Either way is fine. So now what B has is the address of member I of the structure that P is pointing to. Alrighty. So I can see a lot of traffic in the text channel, but this stuff is actually kind of important. So if you got this already, obviously it's okay. Okay, but for people who are trying to get this stuff, it's important to kind of pay attention to what I just said. Alright, so B now has the address of member I of the structure that P is pointing to, but I don't want the address. I want the value of the member. So I need an LDBB in this case, so that now register B finally has the value of member I of the structure that P is pointing to. So that's my right hand side. The left hand side, on the other hand, is super duper easy because printer is a global variable, and to access a global variable, it's at a static location. The label is the location. So that in that case, we just say LDIA. Cannot use B at this point because B is important. It represents the right hand side. So we just say load A with printer the label, and then we say STAB. So that would accomplish printer equals to P points to I. And then the next one, I mean, you guys have seen this already from last Thursday, because last Thursday I was using an infinite loop, where a pointer keeps chasing its own tail. And I was using that as an example to illustrate, okay, in case your program is in an infinite loop, what do? You can type Control C, to basically interrupt the execution of the program, get the partial TSV file, and then you will still be able to analyze, where the loop is. So that's what we did. All right, so at this point, I'm just gonna write the code kind of real quick, like that. And then we have the offset to member P. So we have x underscore P. And then we add AB or BA, doesn't matter which way, so I'm going to do it the same way as before. And this time we have to store it to P, but P is a parameter which is on the stack. So that means it's not going to be as simple as line 58 and 59, because this time I actually have to add the stack pointer to the register before I can use it as an address. So not quite as simple, but not too bad either. So I load A with the offset, add AD so that register A is now the actual address. Then we can store to whatever register A is pointing to, because register A now has the address of parameter P. And then we are going to overwrite it with the right hand side, which is already computed in register B. And that's it. I think that should be that should conclude the whole thing. All right, so I'm getting back to the text channel. Hand tracing is not necessarily a bad thing. I do that with my CISP310 class. Drawing the structure helps, especially if you use a spreadsheet, so you can actually visualize where each member is and why we define the labels the way that we do define the labels. We can overwrite the parameter. So in this case, traverse does say const, but the const does not apply to the pointer itself. The const applies to the structure that the pointer points to. So that means I can actually play with the pointer any way I want, and the compiler is not going to complain about that. Now, if I add another const over here, then the compiler look at this code and go like, this line is bad because I'm updating a parameter that is const. But since I did not have that, right, this const was not there, then I can actually go ahead and change, the parameter. A parameter really has very little distinction compared to a local variable. The only difference is one lives on the positive side of the return address, and the other one lives on the negative side of the return address. I mean, where the return address is in a call frame. I should make it more clear. There we go. Yep. Okay. So Chris said, do I need LDBB after line 65? And the answer is yes, I do. Oh, good job. Yep, I do need an LDBB because register B has the address of member P of the structure that P as a parameter is pointing to. So I need an LDPP because if I did not do that extra LDPP, what I do end up with will be equivalent to putting an ampersand over here. I end up with the address of member P of the structure that P is pointing to. But that's not what I want. I want the actual value of the member. So that's why I need that extra LDBB over here. So good catch, Chris. All right. All right. Yes, negative means at a lower address. So when you compare local variables, they are at addresses lower than the return address, where the return address is in the call frame. Yep, there we go. This is interesting. This as a as a keyword is interesting because this is basically an implicit parameter that is always pushed when you access a method of an object. Well, I shouldn't say always, because if you're dealing with a static method which attaches to the class itself, then there is no this, because this refers to the object itself. All right, so Luke says, isn't there a possible situation where modifying the parameter inside a subroutine B within subroutine A would mess up the parameter if we are using it again in another subroutine C within the same subroutine A? The answer is no, because it is passed by value. Because when you need to call C from A again, A is going to push the parameter again on the stack. It's not reused. So it's not an issue. So it is, so Davesh is correct. Local variables have a lower address, and then we have the return address on the stack, and then we have the parameters. Yes, that is correct. Yep. And then there's the question of, oh, okay, never mind. Okay, I saw some changes. I think it was a message deleted. Okay, all right, so we are good here. All right, so we'll test this code. Okay, we'll test it and make sure that it works. So that's the other question, is how do we know whether this code works or not? So I'll explain that shortly. So this is traverse sll.ttp asm. I'm going to pipe it to xclip-cell clip. There we go. And then we get to the assembler and paste the program in. And make sure that we don't have any errors. The error messages, for the most part, should help you identify what the problem is. And it actually takes some coding to generate the correct error message, or to generate a useful, to detect and generate a useful error message. So all of that stuff, it does take some work. All right, so we're going to download it. And I'm going to give it a shorter name. We'll call it t.csv. There we go. And then we switch back to the terminal screen. And now we want to run it. So this is a good way to start. There we go. And there we go. And in this case, I time it out in 3 seconds. In other words, if logism doesn't terminate within 3 seconds, the process will be interrupted. Now we get to the trace analyzer. Go to sheet 1, and let me get rid of that. And then we have import. Yeah, I know the user interface is not really the best. And then we have t.tsv as the file to upload. Replace, tab, and do not convert. And then import. Sure, I can show the terminal. There you go. And then I'm gonna switch back. Okay, sometimes I do that too, just kind of type in stuff when the keyboard is shifted by one key, left or right, up or down. Alright, so we get to analysis. Okay, so now the question is, how do we know what the program is supposed to do? So the best way to do this is to use GDB. Okay, I'm not sure whether I demonstrated this or not, but it's really the best way to do it. Is to I just use online GDB these days. Some people go to Replit, that works too. Or if you have a Linux environment on your desktop, you can go ahead and just use the tools on the command line interface. So all of that stuff works. So now we go to My Projects. Come on. Alright, it's going there. I can tell the browser tab has that thing that's going left and right. Oh. Alrighty. So it looks like it's stuck. Alright, let me stop the process. Do it one more time. There we go. So now we have traverse SLL. SLL stands for singly linked list. Alright, so now we have this code. It is written in C. C is the language. So how do we know the expected behavior of this program? So there are several ways to do this. Some people can just put a little breakpoint here because this is where we quote unquote actually do the printing. So if you put a breakpoint here, you can actually capture the value of printer, or P points to I. If you want to know what the printer is printing, a better way to put a breakpoint is on the next line, because at that point printer is changed already as a variable. So that's one way to do it. But I'm going to show you another way to do this. So we first click debug. And then what we do is we say we can basically use watch expressions. So we say watch, and then you specify the expression that you're watching, which is just printer. So what this does is every time the expression changes, and this I think it doesn't have to be a simple expression. It can be something that's complex. But every time printer changes, it's gonna GDB is going to have an output, which is going to be it will stop first, and then it will have an output to tell you how it is changed. So when I run the program, I don't even need to set a breakpoint in this case because I have a watch point. So when I run the program, right now it says it goes from 0, which is the initial value, to 5. And then if I type continue, which is C, it will give me the second one, which is it changes from 5 to 1. So the actual output is 5 and then 1. And then the next one is 10, because \A is I think it's 10. And then we have the next one, and then we terminate. So we basically wrote that location 3 times. And oh, I take it back. \A should be that's the 7. So it's 5, 1, and then a 7. So \A is the 7. I'm not sure exactly what ASCII code 7 is corresponding to, why it is a \A, but that's basically what it is. Alright, so we can now expect the same behavior in this particular sequence in the assembly code. So when we go to the trace analyzer, so now we need to go to the assemble tab first, because we want to find out where printer is. So when we go to the assemble tab, we look up where printer is defined. Printer is defined here. So printer in this case has an address of location 03. So when we use the trace analyzer, we can see that column C basically reports back any updates of a RAM location. So we basically, I don't know whether this needs to be done or not, whether it needs to be highlighted, but I'm going to highlight it. And then we can search for that pattern. So we Control F to start up the search. So we are looking for *03 equals to. So we can see how it is updated to 5, and then the next one updates to 1, and then the next one updates to 7. So the assembly code does match the C code in terms of the behavior. And then if I go all the way to the last row, we should observe it's row 792. So to get to there, we just basically go C 798, I think. Okay, maybe. We'll see. Alright, close enough. So we get to here, and we can see the stack pointer did get to 0, which is good because we want the stack to be balanced. And then on line 50, location 555 in hexadecimal should correspond to, oh no, this is not the right one. Okay, right here. So that location should correspond to a halt instruction. So that is at location 55. Yep, so we got that. All right, so so the assembly code, as far as I could tell, is having the same behavior as the C code. Okay, now I can go back and look at the messages. All right. All right, so no questions in the text channel. All right, so what is the time? It is 6:15. All right. Could you look at how the parameters are modified? Okay, absolutely. So that is a very good question, Luke. So in order to understand how the parameters are modified, we need to first understand what the stack looks like when the code runs. So to do that, it is helpful to refer to the C code. So we're going to look at the C code first. Alright, so on the left-hand side, we have the C code. So when we look at the C code, we will start to analyze what the stack would look like. Main has no local variables, so by the time we call traverse, the only things that is sitting on the stack would be the call frame of calling traverse. I'm just trying to figure out what is the best way to document the stack. I'm just going to use mousepad to do it. Alright, so yeah, what you're seeing here is stuff for my mainframe class. Very interesting class. Alright, so here we go. Location FF, is going to be the parameter, which is the address of C initially. And then location FE is going to be the return address to main. We don't know exactly what it is, but it's not important because we just want to know what the stack is going to look like. So when we get to traverse keeps changing, P, and P is at location FF. So we are basically looking at location FF and trying to find out how it is changing. Because of the code and because of the way I define struct X, A, B, and C, we can tell that it should start with the address of A, and then it follows the pointer as a member of A, and then it will end up as B. It will have the address of B, then it will have the address of C, and then it will have null, and that's the exit condition. That's when we get out of the loop. So when we look at the trace, okay, so when we go to the trace, now we want to look up, in column C, things that look like this. Okay, so Control F to start the search. So we're looking at star FF equals 2. So the first update is 08. Okay, this is when we call from main. Okay, so the first change is because we are calling from main. So now we want to see whether location 08 is corresponding to A as a structure. So to do that, to understand that, we just have to go back to the very beginning where A is defined. This is where A is, and A is indeed starting at location 08. So we got that explained. And then the next one should be the location of B as a structure. So when we go to the Assemble tab, we can see where B is starting. B is starting at location 06. So that's what we should be expecting in the trace analyzer. So we just use the down arrow here to go to the next occurrence of asterisk FF equals 2. And this one we can ignore. This is okay. So now we know it is not confining to just column C. It searches all the rows, but across all the columns too. All right, not interested, not interested. There we go. So now it is updated to 06, and then after this, it should update to 04 because that's where C is. So we go to the trace analyzer and then we search a few times because it updates on the other side. Okay, so it is 4. And then the last update should be 0 because the member P of C as a global variable is 0. So that's going to be the last update to that location. So forward, 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 and there we have the 0. So I hope that explains, how the parameter is basically being used as a initialized local variable. And that's basically it. Okay, that really is the main difference between a local variable versus a parameter. A parameter has its initial value specified by the caller. A local variable typically does not have any initial value unless you say int I equals to 3, then you basically are combining the initialization with the declaration of the local variable. So in that case, I would start with the value of 3. But the initialization is inside the subroutine itself. Not the initial value is not coming from outside of the subroutine. All right. Jonathan says, I think in your C code you have to change the traverse param back to A. Oh, because I changed it? Oh, right. Let me see. Right, so I was changing that just to show people that this is something that I can do to the main program in order to test the implementation of traverse. I can also go to con here and add something in addition to p does not equal to 0. So I can basically say, because con is supplied by my code, so as long as my con implementation is consistent with the C definition, the program, your code, which is only implementing traverse, should still match the behavior of the C code after I make changes to cont. So I would do that too. Okay, so I'm gonna make certain changes. I can also change how X is defined. As long as I keep member I and member P to do what they're currently doing, I can do something like this in C. I can add a new member, called A over here, and then over here I have to redefine or change, slightly modify the definition of these things to match the C definition. Your code should not have any sensitivity to how I define struct X. All right, so that's kind of the deal. All right, so any questions about the solution of the previous homework? Okay, we got 2 people typing away, so I'm gonna wait a little bit here. All right, first question: do we get partial credit? Yes, you do, but how much partial credit you get depends on how much of your program is partially correct. In other words, if someone figures out, that the C program is putting, okay, let me check here, because I wrote the program, but I cannot remember the details. So if someone figures out the assembly program outputs 5 and then a 1 and then a 7, and then in the assembly code, that person just decides, I'm just gonna, override or update the printer to 5, 1, and 7, that answer is gonna get a flat 0 because it does not reflect the C code whatsoever. So that's kind of the thing I'm looking for. All right. Next one. If uint8 underscore t was added, would we change xa to 0 and then the rest just change? Yes, that is correct. And then the next one says you get full partial credit if all of your code is partially correct. Yes, you'll get as much partial credit as you possibly can. All right. Yes, you only get 2 points for the first 2 questions. Yep, they are just there to kind of help you transition into this, but also to explain what is volatile. I know that's not an assembly language kind of thing. In a way it is, but in a way it is not. Because if you don't understand what is volatile and you go out and then you start to develop embedded system programs, you might be surprised because you would say, but I did update that thing, but the interrupt surface routine never picked up the changed value. What is going on here? Yep, that has to do with volatile. So it's a very important concept in low-level type of programming. I don't put something into the quiz, that is entirely and utterly useless. Okay, can I show all the stack addresses as I showed a little bit? I'm not sure what you mean by all these stack address. I mean, you guys can do the same trace. I mean, you have the source code and you can do your own trace. So that's the thing, okay? That's the other thing. I think, if there is something that you can do yourself, doing it, you doing it is going to be more helpful for you to learn the material than me doing it and you just observe. So, um, any other questions? All right, we got 2 more people typing. All right. Exercise left to the reader. Yeah, kind of. If you guys start to read the trace, and there's one place and you go like, I have no idea why this location is changed in this particular way, that would be a good question to ask. And I do understand that, in terms of teaching style, there is the spoon feeding teaching style, and then there is also the I'm gonna airlift you to the deep end of the pool and then drop you into the pool, kind of approach. And hopefully I'm kind of somewhere in between. Maybe the pool is shark infested or something like that. Can we go over today's lab? I like that question. Okay, I like that question. Yes, we can. A little bit. A little bit. I don't think tank engines can operate underwater. Alright, so this stuff is done for now. And I am going to zip it up so that you guys get a copy, right? Okay, zip traverse sll.c traverse sll.ttpasm, and then I'm gonna upload it right now. And pin it. There we go. All right. So we still have Jackie typing, but I'm going to set up for the next topic. So I'm going to set up for today's lab. Alright, so today's lab is in two parts. So I want to emphasize that today's lab is in two parts. The first part is just multiple choice stuff for the most part. I think the entire thing is multiple choice. I may be wrong, but it's going to be pretty close. And then the second part is going to be the actual coding, and this one is a little bit longer and more complex compared to the one that you just did, for this homework assignment. So that's why you get a whole week to work on this, which does not translate to procrastinate for 6 days and then suddenly try to get it done and try to ping me, every 5 minutes. No, that probably is not a good way to work on this one. You probably want to start thinking about the code tonight because the lab part 1 is going to get you thinking about the C code first. Okay, you got to understand the C code before you can attack the assembly code. And then the next day, you may not want to sit down and do any actual code, but really just kind of observe the C code and figure out, why the C code is doing what it does. Okay, because in this case, you kind of have to understand all of the concepts first. Okay, and then on the next day, you can start to think about, okay, I'm gonna break up the programming task. I'm gonna do one thing at a time, make sure it is done right before I move on. But how do I structure my coding so that I can focus on just one thing at a time, making sure that it does work, and then we move on. So that would be the kind of the plan of attack here. Is not really just trying to sit down, look at this, look at the C code, look at how similar this code is to the existing programs, and then try to copy and paste the code of my TTPSM sample programs because you recognize certain concepts. That approach probably will not work very well with this code because the idea is I want you to understand the concepts. I don't want you to recognize certain patterns and go like, okay, if it matches this, we apply that. If it matches this, we apply that. I want you to understand the rationale behind everything and then be able to solve the problem because of your understanding. Alright, so Jackie just posted something. Wow, that is cool. I should pay Jackie. But thank you very much for having a full explanation of these things. Very good. Now, I do have to explain this, okay? When you're reading someone's understanding of something, it helps, but it is not as good as you figuring out by yourself. So it is probably more helpful. Now, I'm not trying to put this on Jackie, okay? So don't misunderstand. But it's probably more helpful to understand how Jackie goes in to understand this stuff here. Because that's basically, instead of getting the knowledge, you're getting the meta knowledge, the knowledge to get knowledge, right? So I think that is kind of important, is to figure out, why someone gets this stuff, just kind of, okay, this is, I fully understand what is going on here. And that is really kind of important, and that's also something that's difficult to teach, because people think differently, and certain things come easy to certain people. I'll just kind of put it that way. Okay, well, that's sort of what I said, when I said, okay, comment my code line by line, figure out what is in each register and how it corresponds to the C concepts. That is what I was intending to do, but having that table, helps a lot too. Well, power is not something that is important, nor is suffering. All right. All right. So that stuff is useful. What Jackie has posted is useful, but you still need to understand the concepts, right? So you still understand not only the instructions, how it is done in these examples, but also if you think about it, okay, this is typically how I would do it in the class. But if I say, I can do the same thing, knowing how the stack is organized, I can access the parameters in a different way. You have to be able to understand that too. So it is not going to be, because one thing that I worry about, okay, not worry about, but one thing that I think can possibly happen. There's a difference between me knowing something may happen versus I'm worrying about something. So one thing that may happen, based on what Jackie has just posted, is somebody is going to read it and just memorize the entire thing. Okay? So the problem with memorizing the entire thing is if I just throw, a slight variation into the whole thing, then it doesn't connect anymore, right? So I guess you can call that, learning something that is too specific. Just memorizing this specific case is a little bit, it may not help in the general sense. Okay, so I'm going to stop there and move on to part 1 of tonight's lab. Alright, so it doesn't hurt to, well, I'm going to release the code maybe later because I don't want people to go in and start doing stuff. Not yet. Alright, so this one starts right off with a zip file, and I'm going to open up the zip file first. And it has the usual stuff, right? A C file and an assembly language file. So I'm going to pull the C file. I'm just going to, let me see if I can do this. Alright, so let me see if I can drag and drop. Nope, doesn't like that. Alright, so I'm going to have to open with mouse pad. There we go. Alright. So now we have the C code. And if you look at the C code, it's very similar to the other one. We have a struct X like that, and except the first member is no longer just an integer, it is a pointer to an integer. So as far as the structure is concerned, it's not really that much different. And then we have printer as a global variable, and this time I don't even bother to make it a volatile because it actually works without volatile too. And then we have function f. This is what you need to implement, okay? And then we have main, and then inside main, actually this is not true anymore. I have to, it doesn't really matter to you, but it's not true anymore. Array A is actually a local variable, which means it lives on the stack instead of statically allocated. So let's start with main. Okay, we'll start with the entry point of the program. We have A, which is an array. It is initialized to values -2, 1, and 0, and those are signed. And then we have a local variable that is a structure. Okay, so this is the first thing that we need to stop and think about is how can we do this? Can we have a local variable that is actually a structure? I don't think so. That was actually my answering machine. I just got my answering machine was answering a phone call, so it was my mic probably just picked up that a little bit. There we go. Oh, okay. No, definitely not video games. Nobody's playing video games right now. All right, so so now the question is, can we actually have a local variable? Is m mine, which is basically the mine variable of main, and it is local. Okay, so back to here. The answer machine is done already. So we have a local variable that is of the type struct X. Is that even okay? Well, the answer is yes, okay, because the assembly code actually, there's the assembly implementation of main. So this part is given to you. So you can basically just kind of look at how this is done in the assembly code. And then what we are passing to f is not m mine, which is a structure. We're passing the address of the structure. So exactly, why wouldn't it be okay? I mean, that's perfectly okay. So now we call f with the address of a local variable that is of type struct x. And that particular struct x is also initialized. So it uses a as the first member, and it uses 0, which is null, as the second member. So which one is A and which one is 0? Well, it corresponds to the ordering of the member as listed. So this part is required in C. When you use a initialization for a variable, the order of how you specify the value is going to be in the same order as the member as they are listed in the structure. Alright, so now we get into function f. So function f has a parameter that is a pointer to a struct x. But at the same time, it has its own local variable that is not a pointer to a struct x, but it really is a struct x. The next line is using, so I'm going to spell this out. If you want to write it down, maybe put a time mark, just so that you can get back to this point of the recording. So this line, on the right hand side, we are locating member PV of the structure that prev or previous is pointing to, and then whatever the value of this member PV is of the structure the previous is pointing to, we're just going to add 1 to it. That becomes the right hand side. Okay, this is the entire right hand side. And then what we're going to do is to update the member PV of the structure. This time is not pointed to by anything, it is just my local variable mine. Alright, so you have to think about this a little bit, okay? Based on what we have already talked about, okay? How we define offsets to members of a structure and how to allocate local variables on the stack, this should be doable already. It might take you a little bit of thinking, draw the picture, okay? Try to draw the picture of, how it should look like in this particular call frame. The call frame has the parameter, it has the return address, which is nowhere to be seen here, but we know it is there. And then it has the local variable, okay? So you kind of have to draw a picture of that particular stack. Now, I want you, when you draw that, a call frame, I also want you to pinpoint the members of this particular mine, and that will be based on how we define struct x. So you want to have a very good detailed map of the call frame. At the very base of the call frame is where the stack pointer is pointing to. So you have to kind of think about, okay, do I need to change the stack pointer to allocate for the local variable? And then at the end, do I need to do something to the stack pointer to deallocate the local variable? So you're going to have to think about all of those things, okay? The next one is easier. We're just using prev, which is the parameter itself, the value of prev, to update the member the member PN of the structure that is just a local variable mine. All right. So up to this point, there is a slight variation of things that we have been talking about and using. So try to think about how to implement that. Okay, based on what we have talked about already, you should have enough knowledge to do this already. Then we have this thing here. Okay, it looks a little bit strange, but it's not, because if assuming we know how to get to member PV of the structure mine, then we're just dereferencing it. Okay, so you have to think about which opcode is generally used for dereferencing. Okay, given the address of something, how do I get to the memory location of that? Okay, so you kind of have to think about the instructions, the mnemonics. If this is true, which means PV of mine is pointing to something that is not 0, then I'm going to call f recursively. But this time I'm going to use the address of my own struct x mine to pass to the next invocation of f. Okay, So now you have to think about what are we actually pushing on the stack? What if mine is a really big thing? Okay, what if that structure is really huge? Would that make a difference? What am I really pushing on the stack? So think about that. Okay, kind of think about it before you write the code. And then we get to this part here, which is very generic by now, hopefully. So if you look at this loop, you go like, oh yeah, we can probably just copy and paste a bunch of code. And the answer is, yeah, probably. You can probably just copy and paste a bunch of code from tonight's lab, okay, which is already in the zip file and it is already uploaded to Discord. So the only part that is a little bit tricky, I would say a little bit, just tiny bit tricky, is this one over here. So this one is basically saying we want to get to the value of member PV of the structure that pref is pointing to. Once we get to that value, we treat it as a pointer and then we dereference it. So that specific order is what you need to do in assembly language. Okay, you need to get to the structure first. You get to the first byte of the structure, and then you get to the address of the member in the structure that you want to access. Then you get to the value of the member, and then you dereference that member. Okay, so that would be the sequence of how you want to deal with this particular line. And the current time is, I'm just reminding you, you might want to jot down the time mark because what I just said might be helpful, okay, when you are trying to implement this program. The rest of this program is kind of the same deal that we had already, so it's not going to be a big deal. Yeah, I actually have to think, to how to do this one. But this is a fun one, right? I mean, this is a fun one because it actually makes a linked list, but this time you don't see any ABC as global variables. In fact, you don't, other than, you don't see the linking of the linked list at all. But yet, by the time we get to the while loop, I mean, this loop works only because we have a at least singly linked list. Okay, this is the deal, right? So we talked about this last Thursday. We talked about it today, and so this code is, I mean, ignoring this line here. This code is, I mean, we have done it many times, a few times already. This is the third time we have exposure to this kind of code. But this kind of code, means, implies that we are dealing with a linked list. So now you have to think about, oh, but a linked list needs to have the nodes, right? The structures. Where are those structures coming from? Okay, so that's a question. What is the program supposed to print is the other one. So one thing you can do is just to do what I did earlier. Okay, use GDB and find out what printer is printing or what value goes into the printer variable in this particular loop in what order. Okay, so that's one thing. The second thing is I would also put a breakpoint at the very beginning of F. So this way, at the entry point of F, you can use BT, backtrace in GDB so that you can see all the invocations that are active at this particular time. Because then you can actually see how this is done recursively. Okay, you can see, oh, main is calling F, F is calling F, F is calling F. Oh, okay, so that's how we got to this particular invocation of F. If you're using BT, you might as well also use frame. Okay, FRAME is also a command that you can use in GDB. It allows you to change the current context to an earlier frame so that you can investigate what is in the prev variable in the previous invocation. You can also look into what is in mine, which is a struct X in a previous invocation. So those are very useful tools for you to understand the C code, how the C code works. Because until you know how the C code works, it'll be very difficult to write the assembly code and debug the assembly code. So you got to have a very thorough understanding of the C code before you transition to try to code it in assembly. So that, well, that's a very natural lead to part 1 of the lab. Okay, so if you scroll all the way to part 1 of the lab, this one here. So this lab is really designed to help you figure out what the C code is doing. So this lab does not involve you writing anything in assembly. It is all about the C code. What you learn from this lab is going to be helpful in part 2 because because once you understand how the C code works, then you can think about, okay, so I understand the mechanics in this C program. So now you can just look at each statement, look at each expression, and go like, okay, how do we do this expression? I wrote this code, and it was about 60, close to 70 lines of assembly code, and that has some kind of empty lines and some labels and stuff like that. So it's not really as packed as it can be. Yours is probably going to be a little bit longer because I optimized the use of registers, just so that I don't have to keep loading this and then loading that, loading back again. So I optimized the use of the registers a little bit, and that was about 68, 67 lines or so. So yours is going to be about, I'm going to guess about 80 lines of actual code, but you probably want to do a lot of commenting. Okay, commenting is very important because if you don't comment, you write a code on one day and then the next day you come back to the code and you're going to scratch your head and go like, I have no idea what I just wrote or why I wrote it. So revision control is useful here. Okay, you can use a very crude method of revision control. Just copy the existing file to a different file name. Now you want to do it in a very systematic way. So I personally, if I were to do it this way, I'm going to use the date and also the time as a part of the file name. So this way, I can easily tell, the ordering of the files. So in case I need to go back to an earlier version because I made the change and the whole thing doesn't work anymore, then I can go back to an earlier version. So that's one thing. Right. Okay. So the next thing is, once you understand how the C code works, how do you write this code? Step by step. Okay. So the first thing I would do is really just to do one part here, just one statement, and then put a halt instruction right after that. Okay. And the idea is you want to confirm that the member PV of this local variable mine is indeed updated to the correct value as specified by the right hand side. Because if the implementation of this line is not working, it can be a simple careless mistake like what I just did, forgetting to do LDBB, but it can also be reflecting a misunderstanding of the concepts. Okay, so that would be good to have, good to get that done first. The other way to do this is basically just to do the allocation, and then just ignore the rest and then return back to main. Because if you miss anything, with working with the stack, it is very likely that it cannot get back to the return address, and then it's not going to work. It's not going to return correctly. Okay, so just doing the allocation for the local variable and then deallocation of the local variable and then return, I would call that a good version already, good revision already. If you can do that and confirm, okay, I know I can call, it doesn't do a single thing, but it does return correctly, that's good. Okay, then you can add just one line of code, make sure that you're updating a member of local variable mine correctly. If you can do that, that means this is going to be a piece of cake. It means let's see, this is going to be a piece of cake, and then you just have to go like, oh, once I get to this, I can just do blah to dereference it. Okay, so you want to do this step by step. Okay, the idea is don't try to write a whole lot of code and then try to debug like 10, 20 lines of code at a time. You want to basically just write maybe 3 to 5 lines of code, okay, and then find a way to verify that that code works. Okay, because if you cannot think of a way to verify the code works, that means you may not be understanding the concepts correctly. right? Because if you do understand the concept correctly, you know what the program is supposed to do, and therefore the program is verifiable at that point. Okay, so the idea is go slow. Make sure that you fully understand what the program is supposed to do. All right. The lab key. Yes, I have not released the lab key just yet because I think you guys will like it. And I think this time Aaron could not guess it. He guessed it last time, struct. But I think this time is a little bit harder. Okay, so I'm going to point to it so that you guys can see it. Nope, it's not struct when that would be too obvious. Deception. Decepticon. Okay, I like that. Decepticon. No, it is obsessed. Because if you ask, why would anyone write a program like that, that word came to my mind, obsessed. All right, so I'm going to type it in the text channel, obsessed. There we go. And I'm going to pin it just in case someone comes in late and go like, what is the passcode? Not good. The grading of exam 2 is not good. I've been teaching this extra class for the past 4 weeks, and that has been consuming all of my time because it's a new prep. So hopefully next week, someone is going to take over that class, and then I won't teach that class anymore. Yeah, if you see all the empty choices, you can probably assume the empty choices are not part of are not the correct answer. They are not the correct choice. All right. Well, it is in a week. In a way, making something due in a week is really bad because some people would just kind of procrastinate, and it can be seen as cruel, but that's why I keep telling you guys, don't procrastinate. Alrighty. A struct is basically just a record. I mean, it's not an array. There's no way to get through all the members in the programmatic way. So it's not it is not an array in any form of shape. So, all right. So I'm gonna stop streaming unless there are which lab? Part 1 is due tonight, and then part 2 is due next Thursday. Okay, so Sasha, can you not get into the lab, or you can get into the lab but you can't do it again? There's only one attempt. Right. Oh, okay, I see. Alright, so I'm gonna click update, then you can. Why would you submit so quickly? How can people be done and submit it right away? Okay. Alright, so this lab is really important. Okay, so I'm just gonna say one last thing. I'm gonna nag you guys one more time. Don't try to shortcut the multiple choice questions. Okay, I know you guys know how to shortcut multiple choice questions when you can have an infinite number of attempts. Don't do that. Okay, think it through. Actually use the debugger to help you find the answers, because you're going to have to do it anyway. You're going to have to do it in order to implement the program in assembly. So there's no shortcutting, regardless. So might as well just do it the right way. Use a debugger, analyze the program, and answer the questions the long way, so you'll be ready to work on the assembly code after you're done with part 1. Okay, so I'm just saying this, because I think this is a better way to do it rather than using the, I know how to get around, multiple choice, questions kind of way. So, all right, I'm gonna shut up and go get something to eat.